This is the last part of the Chapter 15 review. So follow along. This is an actual AP free response problem. So this is something like you might see something like this if you take the AP exam in chemistry. So let's take a look. It says, answer the following questions regarding the decomposition of arsenic pentafluoride. So 55.8 grams sample of ASF5 is introduced in the evacuated 10.5 liter container at 105 degrees Celsius. So what's the initial molar concentration of ASF5 in the container, and what's the initial pressure in atmospheres of ASF5 in the container? Okay, so the first thing I'm going to do is the first thing I do all the time when I have, here we go, every time it does this, there we go, 55.8 grams, there we go, of ASF5, right? So all of that over 1, I'm going to find the number of moles. So 1 mole of ASF5 is equal to, I got AS at 74.9, and F, there are 5 of them, times 19. So 19 times 5 is 95 plus 74.9 equals, so I get 169.9 grams of ASF5. Okay, so the number of moles I have here is 0.3284. I carry it out a little bit longer than I normally would. I have 55.85. 55.8 is 3 significant figures, but I'm just going to carry this one out just a little bit longer. This is my number of moles of ASF5. There we go. And that's my starting mole. So it says, what's the initial molar concentration? So you guys know that from thousands of calculations, it feels like, capital M, which is molarity, is equal to the number of moles divided by volume. Okay, that's where we are. So the divided by volume part means that my 10.5 liters, that means I divide this number, there we go, by 10.5, and what I get then for my concentration is, of course, 0.03127, and that's my molarity. Okay, so here I've answered the first part. So the first part is 0.03127 molarity of ASF5. Excellent. So what's the initial pressure? Now this is all going to come down to, and I'm going to switch here and move down a little bit. For II, I'm going to use my PV equals nRT, and it says what's the initial pressure. So that means that pressure equals nRT divided by V. Okay, I have everything I need here. My P is what I'm looking for. That sounded weird. My V is the 10.5 liters. The R, why is this thing taking so long? The R is going to, I'm going to do my pressure in atmospheres. So this is liters times atmospheres over mole Kelvin, like that. My T is 105 degrees Celsius, and then plus 273 equals, what is that, 378 Kelvin, and I need more room. My N is the one I just found up above. Right here is 0.3284 moles. Okay, so that's the number of moles. So let's plug all of that in. Right here is the P equals 0.3284 times R. Okay, I'm going to get rid of this stuff here. times 378 Kelvin. All of that divided by 10.5 liters. There we go. So what does that equal? So let's go through all of it here. 0.3284 times 0.0821 times 378 Kelvin divided by 10.5. So that means I get a pressure of about 971 atmospheres. I round that off to 3 significant figures. So there's my answer for, going back up to II. Excellent. Shouldn't be any problems. Let's continue on. In terms of molar concentration, write the equilibrium constant expression for, okay, so they're all gases. We're looking for the molar concentrations, which means my K equals products over reactants to look like this. Like that. Easy. Good. Moving on. Whoa. Okay, I need to reset this page. There we go. So an equilibrium is established. So this is a different kind of problem. We're used to ice problems. This is going to be ASF5, ASF3 plus F2, like that. I'm used to ice problems where I have X as my change, but this tells me the change. So 27% of that goes away. That is my X. X equals 27.7% of the original. Okay, that means, oops, that means that whatever I started off with and the number of moles, 27% of that decomposes or goes away. So let's start off, let's do this. Calculate the molar concentration at equilibrium. Okay, I got to do a couple of things first. I'm going to start with my molar concentration. So the moles of the starting part are 0.3284 moles. All right, that's what I'm starting with. I'm going to multiply by 277. Okay, so what I do is I take my starting moles, 0.3284 times 0.277, because that's 27.7%. I change it to a decimal and multiply. Now what I get from that, for my starting moles, is I get 909. So this is going to be basically 910 when I round up. So this is the amount, this is what X equals, the amount that's going to be subtracted. So my starting, now I'm just going to do starting moles here. And I subtract this from the number of moles. So here's what I'm getting at the end then. So 2374 is the number of moles I have at equilibrium after I lose 27%. That's a 9 there. Yeah, there we go. But my concentration, though, is what I need. So it's the concentration that's important. So divided by this is the number of moles. I'm going to divide by 10.5. So I divide by 10.5 liters, and then that gives me a concentration of ASF5 of 0.02261. And that's the concentration. Now that means that I'm adding 0.0910, right, of both of these, like that. And then each one of these has to be a concentration, so I'm going to divide each one of these by 10.5. Okay, so what does that equal? Because my K value is going to be whatever these two are, ASF3. You remember what this looks like here. F2, like that, all over ASF5. Now, I need concentrations for my K to work, so I need to divide these two to get concentrations here. I'm going to move this one. Come on, there we go. I'm going to move this one down below so I have room for this. So 0.0910 divided by 10.5 equals, now here's what I get for this, 0.00867, and that's going to be squared. I need more room here. This is turned into a project. You got to keep everything straight. All of my my ice work must end up as molarity for equilibrium, which is what I've done here. So that's concentration for that, and this is going to be the same. So my K equals then 0.00867. That's going to be squared. All of that divided by 0.0232261, like that. And then whatever that equals is going to be the K value. So I'm going to square this one and then divide it by 0.02261, like that. Now what I get at the end here for my K value is 0.00332, like that. Okay, so that's my K value. I think it was asking for the concentration at the end for equilibrium, and that would be the answer for that. Let me scroll back up and make sure I answered the question correctly. Calculate the molar concentration, blah, 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 blah. So this is I, the answer to I. Using molar concentration to calculate the volume equilibrium constant, I did that already. This right here is the answer to II, like that. Okay, next problem, we're just about done, is calculate the mole fraction of F2 in the container of equilibrium. Okay? So the number of moles of F2 is this. I'm going to use a different. There's F2. Mole fraction is moles of one thing. So mole fraction is moles of F2 divided by moles total. Okay, so we know what the moles of F2 is. That's the number of moles of F2. I got that from the previous slide. I'm going to divide that by the total. The total means the moles of ASF5 plus the moles of ASF3 plus the moles of F2. Okay, now these two are going to be the same, so that would be 0.0910 times 2 equals, and that's 0.18. And then I'm going to add that to ASF5. .182. That's what these two are. All I did was take this number here times 2. And then let me jump back one more place to get the number of moles 2374 plus number of moles 2374, like that, plus point. So the whole thing equals this, 419. Okay, so that's the moles total. So I divide that by 0.0910 equals, and I flip that. So mole fraction of F2 equals 0.217. That's it. There's the mole fraction. So 21.7% of that is F2. Thank you for paying attention.